It's time to start talking about heat and heat capacity and formally define exactly what heat is. Okay, so at an elementary level, okay, um, and this deserves some historical context. Uh, we'll give the definition and then we'll talk about a little bit about how it came to come about. But heat, at the end of the day, okay, we define heat to be uh, the energy exchanged okay, so heat is the energy exchanged between objects of different temperature. So when two objects are brought into thermal contact, if they don't have the same temperature, some energy between them will flow. And in reality, okay, we should say the net energy exchanged. Um, okay, if we want to think of it in these terms. So, what we mean by this is this: suppose we have two objects in thermal contact. We'll call this A and B, like maybe two blocks. And let's say that initially block A uh, is at, oh, I don't know, 500 Kelvin, and block B is initially at 300 Kelvin. Okay, so what this means is that because temperature is related to the um, kinetic energy of the molecules, now we haven't really run into situations where the energy is different than kinetic energy. We haven't gone into situations where the internal energy includes potential energy terms, but especially for complex molecules, that can happen. Okay. Um, and one of the things that can happen in complex molecules, when you get up into things like diatomic molecules, O2, N2, and things like that, or more complex, sometimes the energy can go into stretching the molecules. And then because the electric bonds, I should say the chemical bonds, holding the molecules together can start to act like springs. You can actually put a type of elastic potential energy into the molecules. Okay, but we're going to ignore that for the moment. Okay, so even though I've called these blocks, we can still imagine that the energy is still just associated with the random motion of the particles and not going into changing the potential energy of the individual molecules. Okay. But anyway, so what this means is that block A, the molecules in block A have faster, on average, random motions and velocities or speeds than the molecules in block B. Okay. And as a result, what happens is when the molecules in block A that are closest to the boundary uh, start interacting with the molecules in block B, they are going to collide with the molecules at higher speeds, and the molecules in block B are therefore going to gain speed compared to what they had been before, but that goes at the expense of energy from block A. So eventually, because now the molecules at the boundary in block A have less average speed, the molecules that they then kind of bounce around with and interact with right next to them will have less energy available in their collisions, and that effect spreads out through the entire block. Whereas now the molecules in block B, the larger kinetic energy, the average kinetic energy, is going to spread throughout the block, and therefore the temperature in block A will decrease. And if we assume these blocks have the same amount of mass, then especially if they're the same substance, like if they're two, say, steel blocks or bronze blocks or wooden blocks or something like that, then we would have, if they have the same amount of mass, then the final temperature would be the average of the two. And so block A would cool down to 400, whereas block B would warm up to 400. Okay? And then at that point, once you have this, okay, so what this means is that net energy transferred from A to B. Okay? Now, it's still possible for B to exchange positive energy with A, and every so often a random molecule in A will gain energy from an interaction with block B, with a molecule from block B. But on average, that's going to be very infrequent compared to the molecules in block A giving energy to the molecules in block B. So the net energy exchange is going to be from A to B, and therefore we say that heat flows from warm objects to cool objects. Okay? So heat flows from warm objects to cool objects. And then once they're at the same temperature, the random collisions aren't going to have any net exchange, because it's just as likely that block B will give a little bit of energy to block A as it is that block A gives a little bit of energy to block B, and the net energy exchange goes down to zero and the temperature doesn't change. So once we reach this situation where the blocks have the same temperature, they are now in thermal equilibrium. So thermal equilibrium is no net exchange of energy. Technically, no net exchange of heat. Now, since heat is energy, heat gets the units of joules. Okay? Heat has the units of joules. Now, that's the SI unit. There are a few other units that are common, okay, as are the calorie, kilocalorie, British thermal unit, and we will kind of talk about those a little bit. But in SI, we will be calculating in units of joules, okay? So this heat flows from warm objects to cool objects is going to be an extremely important point when we get to the issue of entropy. But for the moment, we can kind of take it as axiomatic. And it comes from our momentary justification for it anyway, comes from the fact that it makes sense that if the molecules in A have more jitter to them than the molecules in B, then when they come into contact, that jittering is going to get transferred to B more on average than any jittering from B gets transferred to A, and therefore B will warm up as a result of accepting energy, and A will cool down as a result of losing energy. Okay? So the idea of heat is just the energy that's exchanged between two objects of different temperature, and it really boils down to the molecular and atomic processes. Okay? So we define uh, the kind of standard unit of heat. Okay. So suppose I have a small container that contains exactly 1 gram of water, pure water, okay? And the temperature is initially at 14.5 Celsius, okay? The unit of the calorie, um, okay? So the unit of the calorie is based on this definition: the amount of heat required to raise the temperature of 1 gram of water from 14.5 Celsius to 15.5 Celsius. Okay. Um, and it turns out that 1 calorie, and I really should be very careful here because um, okay, 1 calorie is 4.186 joules. There's another unit that physicists call the kilocalorie, but sometimes dietitians just call it the calorie with a capital C, which is why I wanted to make sure, and I made sure that the calorie, the C on calorie was lowercase. Um, but this is the food calorie. So when you're reading nutrition labels and a food says it might have 300 calories, okay, 300 food calories equal, one food calorie is 1,000 physics calories, okay? So this is 300,000 regular calories. And if I multiply that by 4.186, okay, then this becomes 1 million joules, okay? So if you eat something that has 300 calories, you've consumed 1,255,800 joules worth of energy. Okay. So, one of the things that we will see is that the energies associated with thermodynamic systems tend to be a lot larger than our typical tabletop mechanical systems, right? So if you go back to things like conservation of energy, and you have a tennis ball and you drop it from tabletop height onto the floor, and you want to know what its kinetic energy is as it hits the floor and things like that, thermodynamic energies will typically be much larger scale than those kind of tabletop mechanical energies. Okay, so we will also see that here in a moment when we talk about boiling water. Okay, so how much energy does it take to boil water, for example? Okay, um, so for SI units, of course, we keep things in joules, but for historical reasons, a lot of textbooks will still talk about the calorie because the calorie was the original way that the idea of heat was initially defined. Okay, so just be aware of that. Okay, so now what about imagine the following? Okay, imagine I have 5 tanks of water. And each tank is successively larger than the last. Okay, so let's suppose, this tank, we've got some water. And so we're going to let all of the initial temperatures for these tanks um, be the same. Okay. And so then the question is, how much heat will be required to raise the temperature of each of these tanks by the same amount? Okay. By the same amount of degrees, right? So if I know how much water I have, can I predict how much heat I will need to raise them by the same amount of temperature? Okay. And so let's suppose that my first tank is, say, 100 grams. My second tank is 500 or 200 grams all the way up to 500 grams. Okay. So we're increasing the mass by 100 grams each time, right? So okay. And so the idea is if all of these, let's just say, are at 300 Kelvin. So they have the exact same initial temperature, and I want to know how much heat. Oh, by the way, there's one thing I really should mention, and that is this: we use the symbol capital Q for heat. Okay, so how much heat is required to bring the final temperature of each system to, say, 400 degrees? Okay, so I need to raise the temperature by 100 Kelvin, right? Um, so this is the same for all the tanks. So the idea being that I expose these tanks of water to some sort of heat bath. Maybe we're talking, kettles of water, and I put them on the stove. The same stove, okay? And I measure the um, amount of heat required to raise them by this same temperature, right? So my mass is going to be my independent variable. And in this case, we're in grams. And I measure the amount of heat required. Now, this is a bit of a difficult thing to do, but in principle, imagine that this is the way it is. Okay. And one way that you would do this, perhaps in principle, in practice, would be to look at your energy meter. Okay. From your electric company, right? And you would have to have all of your other devices off, or you would have to know exactly at what rate they're consuming energy. But in principle, suppose you turned off all of your other devices and you measured the amount of energy that it took from your stove to heat this water in each tank by 100 degrees. So what you would notice, okay, is that this would be a linear relationship. Okay, so this is a linear relationship, and your slope would have to relate your temperature difference, right? Because obviously it would take more heat to raise it to, say, 500 Kelvin or 600 Kelvin. It would take more heat to do that than to just raise it to 400, but this is why we're keeping the temperature constant in this case. But the idea being that the slope, well, let's start here. It should make obvious sense that it would take more heat to heat 200 grams than 100 grams by the same amount. It should take more heat to heat 300 grams than 200 grams, again by the same amount of temperature, and it should take 400 grams more heat to change its temperature than 300 grams, and so on. Okay, so it shouldn't be any surprise that it takes more heat the more mass you have. Okay, so the first conclusion to be drawn is that the amount of heat required is proportional to your mass. Okay? The amount of heat required is proportional to your mass, and that means your slope has to be the constant of proportionality. So we have Q would equal some sort of constant. Let's call it K, for example. The amount of heat required would be K times M. But K must also depend on your delta T. Because the more temperature difference that you're trying to achieve, the more heat you have to have. So your proportionality constant K is actually made up of two terms. Another constant and delta T. And this proportionality constant C is what we call the specific heat. Okay? And what this means is, and by the way, we typically write this like this. Okay? We typically write this equation like this. This is the equation that defines heat capacity for a substance. So C is called the specific heat, and C represents the amount of heat um, the amount of energy required to raise, I really should say to raise the temperature of a given amount of mass by a certain increase in temperature. Or it doesn't even have to be increase, it could be decrease, but by a certain amount. Okay. So C must have units of joules per kilogram per degree Kelvin. Okay. Um, Now, I really should specify that um, C is actually temperature dependent. Okay. C is actually a function of T, but for large ranges of T, this tends to be more or less constant. So for most purposes, we take the specific heat of a substance to be constant. Okay. So what this means is that C represents the amount of heat that would be required to raise the temperature by a given amount. Okay. Now you can also lose heat this way. Okay. But we define it in terms of gaining heat. Okay. And so this idea of specific heat is an experimentally determined value. Okay, it kind of pops out of this kind of consideration of the fact that this kind of experiment tends to give you a linear line when you measure the same kind of temperature increase for the same kind of substance, just with different masses. But that's still an experimentally verified claim. Okay, so C, the specific heat, is a experimentally verified value, and with that, there are a lot of tables, okay, that you can reference for finding specific heats. And in the OpenStax textbook, it happens to be in section 1.4 of volume 2. So we will allow you to reference that table for, uh, and by the way, this is university physics. Okay. So OpenStax University Physics Volume 2, Section 1.4 gives you the table of some common specific heats. Okay. Um, Now, the specific heats to take note of, okay, is water, and the specific heat of water is 4,186 joules per kilogram. Now, the textbook denotes this as degrees C instead of Kelvin, but remember that delta T is the same for both degrees C and Kelvin scales. Okay, so even though 100 Celsius is 273 or 373 rather, 373.15 Kelvin. When you go up by increments, they still have the same incremental value, right? So it doesn't matter if you're using joules per kilogram degrees Celsius or joules per kilogram Kelvin, you're going to get the same increment for delta T, right? But some general things to note from the table, if you reference it, um, a lot of your metals have relatively low C compared to water. Okay, and this is because typically metals are very conductive. They have a unique valence electron structure compared to a lot of other materials. And that valence electron structure allows things like heat and electricity to flow really well. So it doesn't take as much energy to excite those valence electrons and let them start moving through the materials much more efficiently than it does something like water, where the electrons are a little bit more tightly bound. Okay, so because remember, this is agitation of the molecules and the atomic particles. So the better and easier you can agitate those, the more readily heat is going to flow into or out of a substance. So your metals, if they're typically, this is not universally true, but it's often true. It's a good rule of thumb. If you have a metal that is electrically conductive, then it will often be thermally conductive, more thermally conductive relative to water than a lot of other things. Okay, so a lot of your metals have relatively low specific heats. The human body, because the human body is a lot of water along with some other chemicals, you know, uh, carbon specifically, and so forth. It's actually close to water, but it's not quite as high because we also do have impurities that help make our bodies electrically conductive. And I don't mean impurities in the sense of your body being impure. I mean chemical impurities relative to water. Okay, so like ionic compounds and things. Um, and so the human body is roughly 3,500 joules per kilogram degrees Celsius. Wood is decently high at 1,700. But then when you get into your liquids tend to be on the higher side with a few exceptions. And the reason being that when you're in liquid state, your bonding is a little bit different than it is in the solid state. So your molecules have to travel a little bit further before they start colliding with other things, and so it's not going to be it's not as thermally conductive on average, because your density is also a little bit lower as well. So the lower your density, the further your molecules have to travel before they collide into things. And so it takes a little bit more energy as a result of that to raise the temperature. Where things are more tightly bound and also have good conductivity, then you have lower specific heats. Okay. Um, and then with gases, it just tends to depend on the nature of the gases. Okay. As to their conditions, right? How compressed is the gas? At what initial temperature is the gas, and all of these sorts of things. So we're not going to worry too much about that, but do understand that for gases, it's a little bit more complicated than it can be for solids and liquids. All right. So let's do an example. All right. Let's do an example here. So suppose um, that, oh, I don't know, let's say iron. Okay. Let's say I have a 1.5. I have a 1.5 kilogram block of iron, and it's initially at 300 Kelvin. Um, and its specific heat is 452. And I want to know how much heat will be required to raise the temperature to 500 Kelvin. Oop. So we just start with this equation. And so note that our delta T is 200 Kelvin. This comes from 500K minus 300K. And that's the same thing as 200 degrees Celsius. Okay, the temperature change would be the same total amount of change on either the Celsius or Kelvin scale. And so now we can just plug everything in. So this is going to be 1.5 and C is 452. Joules per kilogram per Kelvin, and my delta T is 200 Kelvin. Okay. And so we now plug this into our calculator. And we're going to get 1.5 times 452 times 200. And this is 1.36 times 10 to the fifth joules. Okay, so it took 135,000. The exact number is 135,600. Rounding that to 3 sig figs is 1.36, 136,000. So 136,000 joules of energy, okay, went into heating this iron block, okay? And so, as another example, and one that, probably hits home for a lot of folks, is suppose I have Um, 1 kilogram of water. Well, hang on just a second. Let's actually check this out. Um, okay, so let's suppose we have 3 cups of water. And, man, that almost looks like a W. Okay, so 3 cups of water is approximately um, 710 grams. So that's 0.710 kilograms. Okay. And suppose the initial temperature is 20 degrees Celsius, and I want to boil the water. So I need to bring the water up to 100 degrees Celsius. How much heat do I need to add to the water? Okay. And you might recognize this, okay? You might see where I'm going with this. Boiling 3 cups of water is how you make ramen soup, all right? So, a staple of college students everywhere. So, my heat required to make my ramen soup uh, is going to be 0.710 kilograms times the specific heat of water, which we've already stated as 4,186 joules per kilogram per degree Celsius. And we're going to multiply that by our temperature difference of 80 joules, or 80 degrees Celsius. Okay. And plugging all of this in, we're going to get 0.71 times 4,186 times 80 . 2.38 times 10 to the fifth joules, 238,000 joules. Okay. So think of this whenever you turn on your oven or your stove, okay? And what's happening in reality is that your burner typically will actually produce or generate, uh, try to transmit more energy than that because some of it is lost to the environment. Very rarely will all of the energy from the stove be directly transmitted to the pot or pan and hence the contents of that pot or pan. Um, it will also go into heating the environment, right? So your stove is actually generating more energy than that over the time period that your noodles or your water will come up to a boil. Um, but that is the amount of energy that has to be transferred into the water, minimum. Okay. That is the minimum amount of energy that has to be transferred into the water for it to boil. Okay. So in the next video, we will look at pressure changes, or not pressure changes, but phase changes, and talk about going from solid to liquid phase, or from liquid to solid phase, or from liquid to gas phase, or gas to liquid phase. Okay. But there will be a similar kind of process that happens. The only difference with phase changes is in the immediate instance where you're changing phase, your temperature doesn't change. So the amount of heat that's required is not going to be temperature dependent, just mass dependent. Okay. Actually, so as a matter of fact, we can actually address that issue immediately. So let's actually talk about that here. This is what we call latent heat. Okay. But the same kind of concept occurs. This is a linear relationship between heat and mass, and therefore you'll have a proportionality constant. So the amount of heat required to change an object's phase or a substance's phase is going to be equal to the mass of that substance times a proportionality constant that we call L. So we have what we call the latent heat of fusion. And the latent heat of vaporization. So your latent heat of fusion is the phase change from solid to liquid. And the latent heat of vaporization is the phase change from liquid to gas. Okay, and by the way, this is also vice versa. So when you go from a solid to a liquid and you're raising the temperature, you have to absorb heat. And if you are going from a liquid to a solid, you're going to release heat, right? And then same thing for the latent heat of vaporization. When you go from a liquid to a gas, you need to absorb heat because you need to get hotter, so you have to absorb temperature. You have to absorb energy, and when you go from a gas to a liquid, you're generally going to be losing temperature after that process. And by the way, I said that this is temperature independent. This is at the point where the phase change occurs, and that is temperature independent. But generally, once you go from a solid, let's go from a let's look at the latent heat of vaporization from liquid to gas. Okay, so for example, water. The boiling point of water is 212 Fahrenheit or 100 Celsius. Liquid water cannot go beyond that. So even if you have a stove, let's say at 300 degrees Fahrenheit, and you put a pot of water on it, the water itself will not reach 300 degrees Fahrenheit. It will boil and it will become steam before it can increase in its temperature. Once it is steam, it can increase in its temperature, but the liquid form of water cannot. Okay? So, generally, when you're going from liquid to a gas, you're going to um, need heat to increase the energy in the substance to break the bonds that make it in liquid form and allow the individual molecules to then become gaseous. So that requires an increase in heat, and then you can increase the temperature from there. Okay. So, for example, the latent heat of vaporization for water is in joules, and so, by the way, L is going to be measured in joules per kilogram because we're not changing the temperature of the water at the phase change. We're just raising or introducing an amount of heat that allows the phase change. And the latent heat of vaporization, well, let's put it this way. LF will typically be denoted as the latent heat of fusion, and LV will be the latent heat of vaporization. So for pure water, the latent heat of vaporization is about 2.26 times 10 to the sixth joules per kilogram. Okay, so if we go back to our previous example of the boiling water, it took uh, just a little over or a little under 250,000 joules to boil the water, right? Bring the water to a boil. So now the question is, how much heat is required to evaporate all the water? Okay, so now our heat of vaporization is going to be the mass of our water, 0.710 kilograms, times 2.26 times 10 to the sixth joules per Kelvin, or kilogram rather. My kilograms cancel, and if we plug this in, we get 0.71 times 2.26 times 10 to the sixth, and we obtain 1.605 times 10 to the sixth joules. Okay, so to completely boil the water away requires over 1,000,000 joules of energy. Okay, so if I added these two numbers together, the sum of these two numbers would be the total amount of heat that would be required to take 3 cups of water at 20 degrees Celsius, or roughly room temperature, up to boiling, and then completely change the phase into gaseous form. Okay, it's well over 1,000,000 joules. It's almost 2,000,000 joules when you add it all up. It's about 2.83 joules, 1.83 million joules. Okay, 183,000 joules, 1,835,000. Okay, so a lot of energy compared to a lot of the kinds of mechanical systems that we explored in our regular mechanics of conservation of energy and conservation of momentum at the tabletop scale. Okay, so just be aware that your thermodynamic systems are going to be fairly extreme in their energies comparatively. Okay, so that is a little bit about heat capacity and the latent heat of fusion and vaporization. And hope you enjoyed, and we will see you in the next lecture.